In a universe of seemingly infinite scale, where galaxies spiral across the cosmic expanse in numbers beyond human comprehension, it remains a profound curiosity that the thing we search for most desperately is ourselves. We scan the heavens not merely to catalog distant worlds, but to discover whether we stand alone in the vastness of space and time. Are we a cosmic accident, a singular fluke of chemistry and chance? Or does life, in its infinite tenacity, emerge wherever conditions allow? Just 40 light-years away, a distance that sounds immense yet represents merely a stone's throw in cosmic terms, lies a tiny, dim star nestled within the constellation of Aquarius. This star, catalogued as TRAPPIST-1e, appears cold, ancient, and barely visible to even our most sophisticated instruments. It burns with a feeble light, a mere whisper compared to the brilliant radiance of our own Sunday. Yet this unremarkable stellar ember hosts something truly extraordinary, something that has captivated astronomers and exobiologists alike. Orbiting this diminutive star are not one, not two, but 7 Earth-sized planets, arranged in a cosmic architecture that seems almost deliberately designed for our study. It is as if nature itself constructed an elaborate experiment, a laboratory in the cosmos where the fundamental question can be tested. Can life exist around a star so different from our own? Can worlds orbiting a red dwarf, a stellar type that comprises the vast majority of stars in our galaxy, harbor the conditions necessary for biology to take hold? These are not abstract philosophical questions. They cut to the very heart of our place in the universe. One by one, as astronomers have turned increasingly powerful instruments toward this distant system, they have systematically ruled out most of these worlds as candidates for habitability. The innermost planets orbit too close, their surfaces scorched by the star's radiation despite its comparative dimness. Too hot, the data suggests. The outer worlds drift too far from their stellar parent, receiving insufficient energy to maintain liquid water on their surfaces. Too cold. Some show no evidence of atmospheric retention, their protective blankets of gas stripped away by stellar winds and radiation. No atmosphere, no chance. But one world continues to hold promise, refusing to be dismissed as easily as its siblings. TRAPPIST-1e, the 4th planet from the star, occupies a position that astronomers describe with cautious optimism. Thanks to data streaming back from the James Webb Space Telescope, humanity's most advanced observatory ever deployed, we may finally have obtained our first glimpse of this world's atmosphere. What astronomers have found in those spectral lines and absorption features is nothing short of astonishing. Could this distant world, locked in its tight orbit around a dying ember of a star, represent the first true Earth-like planet discovered beyond our solar system? Could TRAPPIST-1e, against all odds, host life? These questions drive the current age of astronomical discovery, propelling missions and observations that push our technology to its absolute limits. To understand the significance of TRAPPIST-1e, we must first comprehend the nature of its stellar parent. TRAPPIST-1 is classified as an M8 class red dwarf, placing it at the cooler, dimmer end of the stellar spectrum. Only slightly larger in diameter than Jupiter, the largest planet in our own solar system, this star produces 1,800 times less light than our Sunday. To grasp this difference in luminosity, imagine comparing a single candle flickering in the darkness to the banks of floodlights illuminating a college running track. The disparity is that profound. Although the star itself was first discovered in 1999, catalogued as an unremarkable dim point of light among millions, its full planetary retinue wasn't revealed until 2017. That year marked a watershed moment in exoplanetary science when TRAPPIST-1 became the first, and to this day, the only planetary system to be discovered by the TRAPPIST Optical Robotic Telescope network. This specialized instrument comprises 2 components working in concert. TRAPPIST South, positioned high in the Chilean mountains where the air is thin and the skies remain dark, and TRAPPIST North, situated among Morocco's ancient Atlas Mountains. These telescopes employ a technique called transit photometry, a method that has revolutionized our ability to detect distant worlds. The principle is elegant in its simplicity. As a planet passes between us and its parent star, some of the star's light is blocked, causing a measurable dip in the star's apparent brightness as observed from Earth. By taking multiple observations over extended periods, astronomers can isolate the periodic signatures of individual planets, each creating its own distinctive pattern of transits. Initially, the data analysis revealed only the 3 innermost planets, each leaving its telltale shadow as it crossed the face of TRAPPIST-1. But as additional data accumulated from both TRAPPIST telescopes, supplemented by observations from the Spitzer Infrared Space Telescope orbiting high above Earth's atmosphere, this total climbed to an unprecedented 7. More remarkably still, these worlds are all rocky in composition, terrestrial planets rather than gas giants, and all measure roughly Earth-sized. This makes TRAPPIST-1 host to the largest collection of Earth-like planets found around any single star, a planetary system that mirrors our own inner solar system in unexpected ways. Yet this discovery immediately raised a profound question. With such a small, dim star at the center of this system, could any of these worlds truly be habitable? Could they receive enough energy to maintain liquid water, that essential ingredient for life as we understand it? The answer requires these planets to orbit much closer to their star than Earth orbits the Sunday. In the TRAPPIST-1 system, the planets certainly meet this requirement. All 7 worlds huddle close to their stellar parent in orbits that would fit comfortably within the distance between our Sun and Mercury. TRAPPIST-1e specifically orbits at merely 1/13 of Mercury's orbital radius. This extreme proximity to its star carries significant implications. The planet is likely tidally locked to its host star, with the same hemisphere perpetually facing the star, while the opposite side remains in eternal darkness. This configuration mirrors our own moon's relationship with Earth, where we always see the same lunar face. For a potentially habitable world, tidal locking presents both challenges and opportunities that scientists continue to explore and debate. Yet despite this unusual orbital arrangement, TRAPPIST-1e's distance places it precisely in the middle of the predicted habitable zone, that narrow band where a planet receives neither too much nor too little stellar energy. TRAPPIST-1e absorbs approximately 2/3 of the energy that Earth receives from our Sun, a value that falls well within the range scientists consider potentially conducive to life. This positioning is exactly why scientists have focused so much attention on this particular world among the 7 siblings. But stellar radiation alone cannot sustain life. TRAPPIST-1e would almost certainly require an atmosphere, a protective envelope of gases that could moderate temperatures, shield the surface from harmful radiation, and potentially provide the chemical building blocks necessary for biology. This atmospheric question is precisely what scientists have been investigating using our most powerful space-based observatory, the James Webb Space Telescope. The teams involved in developing the James Webb Space Telescope were rewarded for their efforts with guaranteed observation time, allowing them to pursue their most ambitious scientific goals. One particular research group, operating under the unwieldy but apt designation, the Deep Reconnaissance of Exoplanet Atmospheres through Multi-Instrument Spectroscopy, or more memorably, the DREAMS team, immediately set their sights on the TRAPPIST-1 system. The James Webb Telescope possesses unique capabilities that make it ideally suited for this investigation. Its sensitivity and precision exceed anything humanity has previously deployed, allowing it to detect spectral signatures from the thin band of gas that constitutes a planetary atmosphere across a gulf of 40 light-years. Webb accomplishes this remarkable feat through a technique called transmission spectroscopy. As an exoplanet passes in front of its parent star from our perspective, the telescope measures not only the drop in brightness, but also subtle changes in the spectrum of light that reaches us. Some of the starlight passes through the planet's atmosphere, if one exists, and different atmospheric molecules absorb specific wavelengths of this light. The telescope's near-infrared spectrometer designated near-spec in the efficient shorthand of aerospace engineering, measures wavelengths of infrared radiation closest to the visible spectrum. Molecular bonds absorb energy within this range, and crucially, different chemical bonds absorb at different specific wavelengths. A carbon-hydrogen bond in methane absorbs at one set of wavelengths, while a carbon-oxygen double bond in carbon dioxide absorbs at another distinct set. By measuring precisely which wavelengths are absorbed as a planet transits its star, astronomers can first determine whether an atmosphere exists at all, and then identify which specific gases comprise that atmosphere. The TRAPPIST-1 system has proven particularly amenable to this type of analysis. Counterintuitively, the very dimness of the star that might seem like a disadvantage actually enhances our measurements. The data astronomers have obtained from TRAPPIST-1 is 10 times more sensitive than measurements from any other known planetary system. Why does this dimness help? When a planet obscures a portion of a dim star's light, it causes a proportionally larger drop in the star's apparent brightness compared to the same-sized planet passing in front of a large, brilliant star. This larger relative change in brightness is correspondingly easier to measure with precision. Using these sophisticated measurements, the research teams have already made significant progress in characterizing the TRAPPIST-1 planets. They have definitively ruled out the possibility of substantial atmospheres on TRAPPIST-1c and TRAPPIST-1d, two of the neighboring worlds. But the results from observations of TRAPPIST-1e, a rocky planet measuring approximately 0.9 times the diameter of Earth, proved so intriguing that scientists found themselves unable to dismiss them. The data suggested that this planet might, in fact, possess an atmosphere, a finding that carries profound implications. This evidence was more than sufficient motivation for the DREAMS team to dedicate all of their guaranteed James Webb observation time to this single question. So far, they have observed 4 separate transits of TRAPPIST-1e across the face of its parent star, each observation adding to their dataset and refining their conclusions. But what precisely have these observations revealed? Scientists can begin by eliminating several atmospheric possibilities based on what the data does not show. TRAPPIST-1e almost certainly does not possess a primordial atmosphere, the type of atmosphere a planet is born with during its formation. These primordial atmospheres are typically dominated by light gases, particularly helium and hydrogen, remnants from the protoplanetary disk of gas and dust from which the planet coalesced. No signatures of these light elements have been detected in the spectroscopic data. They were likely stripped away by the star's intense radiation during the early, more violent phases of the stellar system's history. Nor does TRAPPIST-1e appear to possess a thick, carbon dioxide-dominant atmosphere similar to Venus, where crushing atmospheric pressure and a runaway greenhouse effect have transformed the surface into a hellish landscape. The spectral signatures don't match this scenario. Similarly, an atmosphere like Mars, thin and tenuous with a surface pressure less than 1% of Earth's, seems unlikely given the recent measurements and their implications for atmospheric mass. Remarkably, the elimination of these atmospheric types represents good news for the possibility of life. None of these atmospheric configurations, whether the hydrogen-helium envelope of a primordial atmosphere, the crushing carbon dioxide blanket of a Venus-like world, or the wispy remnant atmosphere of Mars, seem particularly conducive to supporting life as we understand it. So, what type of atmosphere might TRAPPIST-1e actually possess? Here, the data becomes truly exciting, hinting at possibilities that could reshape our understanding of habitable worlds. There exists a possibility, supported by the spectroscopic evidence, that TRAPPIST-1e has developed an Earth-like atmosphere. Such an atmosphere would be dominated by a heavier molecular gas, such as nitrogen, comprising the bulk of the atmospheric mass, with a strong greenhouse effect provided by secondary gases including water vapor, carbon dioxide, or methane. An atmosphere of this type, with a surface pressure around 1 bar, equivalent to the atmospheric pressure at Earth's sea level, might be capable of sustaining sufficient heat transfer to the permanently dark hemisphere of the planet to allow a global surface ocean to exist, despite the planet's tidally locked state. Were this atmospheric configuration to be confirmed through additional observations, the discovery would generate headlines across the world and mark a turning point in humanity's search for life beyond Earth. However, scientists must remain cautious about reaching such momentous conclusions prematurely. The data, while suggestive, slightly favors an alternative interpretation, that TRAPPIST-1e is a cold planet without a global ocean, its water perhaps frozen or confined to limited regions. Correctly analyzing this data represents the critical difference between making the astronomical discovery of the century and committing an embarrassing scientific error. The spectroscopic signatures are subtle. The measurements are at the very edge of even James Webb's capabilities, and multiple atmospheric models can potentially explain the observations. This is where rigorous scientific methodology and careful statistical analysis become paramount. The alternative atmospheric scenario centers on methane, that simple hydrocarbon molecule comprising one carbon atom bonded to 4 hydrogen atoms. High concentrations of atmospheric methane could create what scientists term a reverse greenhouse effect, a phenomenon quite unlike the warming greenhouse effect we experience on Earth. TRAPPIST-1 has a surface temperature of approximately 2,400 Kelvin, dramatically cooler than our sun's surface temperature of 5,670 Kelvin. This temperature difference means that the star emits a greater proportion of its energy in the near-infrared wavelengths rather than visible light. Atmospheric methane possesses the ability to absorb this near-infrared radiation before it even reaches the planet's surface. The methane molecules, excited by absorbing this energy, subsequently re-emit it, often directing it back into space rather than toward the surface below. The result would be a cooler atmosphere than might otherwise be expected, and for the tidally locked TRAPPIST-1e, this could mean that liquid water exists only on the dayside surface, the hemisphere permanently bathed in the star's ruddy light. No global ocean would exist in this scenario, with the night side remaining perpetually frozen. Yet even this configuration doesn't necessarily spell doom for the possibility of life. Such conditions could actually satisfy what's known as Darwin's warm little pond hypothesis for the origin of life, named after Charles Darwin's speculation in an 1871 letter that life might have originated in a warm pool rich with various chemical compounds. Localized bodies of liquid water on the day side, fed perhaps by ice melting at the terminator boundary between day and night, could provide suitable environments for the chemistry of life to begin. Atmospheric modeling studies have lent support to this scenario. Computer simulations of TRAPPIST-1e's potential climate suggest that even if the planet has limited water reserves, or if much of its water remains frozen on the dark hemisphere, it could still maintain a stable atmosphere. The constant illumination of the day side could drive atmospheric circulation patterns that transport heat toward the night side, preventing the complete freeze-out of the atmosphere that would occur if gases began condensing and snowing out on the dark hemisphere. This situation might lead to what planetary scientists have termed terminator habitability, a scenario where life could only establish itself across a dynamic band of territory in perpetual twilight, the boundary zone that separates the eternal day from the eternal night. In this twilight zone, temperatures would remain moderate, neither too hot nor too cold, and the unusual lighting conditions might even prove advantageous for certain types of photosynthetic life adapted to make use of the star's predominantly red light. But liquid water on the surface, whether globally distributed or confined to the day side, isn't the only possibility for habitability. Scientists know that TRAPPIST-1e is rocky in composition, but beyond this basic categorization, much remains unknown about its internal structure. The planet might be an icy volcanic world harboring a subsurface ocean, similar to Jupiter's moon Europa or Saturn's moon Enceladus in our own solar system. Both of these frozen moons conceal vast oceans of liquid water beneath their icy crusts, kept liquid by tidal heating from their giant planet hosts. On Earth, some scientists believe life may have first emerged near deep-sea hydrothermal vents, where superheated water, rich in dissolved minerals, erupts from the ocean floor, providing both energy and raw materials for the earliest organisms. The same process could potentially occur on TRAPPIST-1e if subsurface oceans exist. Life might flourish in these hidden seas, completely independent of conditions on the surface, never seeing the red glow of TRAPPIST-1 the sky above. No matter where water exists on TRAPPIST-1e, whether in surface oceans, twilight zone ponds, or hidden subsurface seas, the potential for life remains. An energy source exists in the form of the star's radiation or internal heat. The spectroscopic evidence suggests an atmosphere might provide the chemical building blocks necessary for organic chemistry. The basic requirements for life as we understand it could all be present. However, scientists cannot yet completely rule out a far more pessimistic scenario, that TRAPPIST-1e is simply a cold, barren, airless marble devoid of any atmosphere whatsoever. The spectroscopic signals are subtle, potentially explicable by other phenomena, and the measurements remain at the limits of current technology. More observations are needed to resolve this fundamental uncertainty. This uncertainty leads directly to a discussion of what factors could prevent a stable atmosphere from forming and persisting over billions of years. Ironically, the very thing that makes TRAPPIST-1e potentially habitable, its proximity to its star, also poses perhaps the greatest threat to its habitability. The red dwarf star TRAPPIST-1 itself may have signed the planet's death warrant even before life had a chance to begin. Imagine standing on the surface of TRAPPIST-1e for a moment, if such a journey were possible. Looking upward, the star would appear more than 4 times as large in the sky as our Sun appears from Earth, a massive ruddy disk dominating the heavens. The star would glow with a deep red-orange color, casting everything in the hues of perpetual sunset. For creatures evolved on Earth, adapted to the yellow-white light of our Sun, the landscape would appear strange and alien, yet hauntingly beautiful in its own way. Red dwarf stars, despite their small size and low luminosity, are extremely active stellar bodies. They produce more powerful flares than our Sun, and these violent outbursts occur far more frequently. The worst recorded geomagnetic storm ever to strike Earth was the Carrington event of 1859, when a massive solar flare and coronal mass ejection slammed into our planet's magnetic field, inducing electrical currents strong enough to shock telegraph operators and set telegraph paper aflame. This represented a greater than 1 in 100-year event for our Sun, an extreme occurrence. TRAPPIST-1, by contrast, is believed to release a flare of this magnitude more than once every 2 days. Standing on the surface of TRAPPIST-1e, you might actually be able to watch solar flares, enormous arcs of plasma, erupting from the star's surface and extending into space in real time, a spectacular but terrifying sight. These flares carry enormous amounts of energy toward any orbiting planets, energy delivered in the form of high-energy particles and intense radiation. Over geological time spans, this relentless bombardment could strip away a planet's atmosphere entirely, molecule by molecule, making life as we know it all but impossible. This assumes, of course, that the atmosphere was permitted to form in the first place. Red dwarf stars possess remarkably long lifespans compared to larger, brighter stars. TRAPPIST-1 is expected to continue burning for 10 trillion more years, 700 times the current age of the entire universe. By comparison, our Sun likely has only 5 billion years remaining before it exhausts its hydrogen fuel and expands into a red giant, eventually consuming the inner planets, including Earth. This extreme longevity might seem advantageous for the development of life. Surely, given such vast stretches of time, life would find abundant opportunity to emerge and evolve. But the reality is more complex. Because red dwarf stars live so long, their chaotic and energetic juvenile phase, the stellar equivalent of a violent adolescence, lasts correspondingly longer. For hundreds of millions or even billions of years, a young red dwarf bathes its planets in intense ultraviolet radiation and X-rays, punctuated by frequent, powerful flares. It is precisely during these formative years that some planets begin generating their own secondary atmospheres, slowly replacing whatever primordial hydrogen-helium envelope they may have possessed with atmospheres composed of heavier molecular gases. These gases, including carbon dioxide, nitrogen, water vapor, and methane, are released from the planet's interior through volcanic activity. As the planet's interior churns and roils, driven by radioactive decay of heavy elements and residual heat from its formation, volcanoes erupt, venting gases that accumulate to form an atmosphere. The problem for planets orbiting red dwarfs becomes apparent. If the aggressive atmosphere stripping phase lasts too long, if the stellar bombardment continues unabated for too many millions of years, then an Earth-sized planet might not contain sufficient volatile elements within its interior to fully generate and maintain a stable, life-supporting secondary atmosphere. The planet engages in a losing battle, continuously generating atmospheric gases through volcanism, even as stellar radiation strips them away. Eventually, the volcanic outgassing slows as the interior cools and the reservoir of volatile elements depletes, but the stellar assault continues. Scientists have calculated that if a planet's atmosphere isn't firmly established before approximately 5 billion years, it may never successfully generate one, condemned to remain airless throughout the remaining trillions of years of its star's life. A death sentence issued before the planet ever had a chance to live. At this point, the prospects for TRAPPIST-1e might seem rather hopeless, and you might reasonably wonder how this world ranks as one of the most promising candidates for habitability among known exoplanets. The answer lies in the fundamental uncertainty that still surrounds this world. Scientists do not yet know definitively whether an atmosphere has survived the stellar onslaught or not. The spectroscopic hints suggest its existence, tantalizing but not yet conclusive. Moreover, the star's violent outbursts, while potentially destructive, may also prove completely necessary for life to begin. Ultraviolet radiation from stellar flares may be essential for creating RNA building blocks, complex organic molecules that are central to the metabolism of every life form ever discovered on Earth. Laboratory experiments have demonstrated that UV radiation can drive the synthesis of nucleotides, the molecular units that link together to form RNA, from simpler precursor chemicals. Without this energetic radiation, the origin of life might be significantly more difficult, or even impossible. Now that TRAPPIST-1 has entered its calmer main sequence phase, having passed through the tumultuous violence of its youth, it produces lower levels of UV and X-ray radiation than during its juvenile past. There exists a genuine possibility that a stable, potentially habitable atmosphere could exist on TRAPPIST-1e, having weathered the storm of the star's adolescence and now persisting in a more benign radiation environment. Furthermore, any atmosphere that does exist could possess protection from continuing stellar flares through the planet's own magnetic field. Functioning much like Earth's magnetic field shields our atmosphere from solar wind. Earth's magnetic field exists because the planet's outer core consists of a moving mass of molten iron and nickel. As this electrically conductive fluid flows in complex patterns driven by the planet's rotation and internal heat, it generates electrical currents. And these currents in turn produce the magnetic field that extends far into space, deflecting charged particles from the sunday. There is good reason to believe that TRAPPIST-1e possesses a similar system. The planet's size and composition suggest it should have a substantial iron core, and depending on its internal temperature and the presence of heat-generating radioactive elements, this core could remain at least partially molten. In fact, TRAPPIST-1e's extremely close orbit to its star could actively help maintain its magnetic field through a process called tidal heating. If TRAPPIST-1e's orbit possesses even slight eccentricity, meaning its distance from the star varies over the course of each orbit, this would cause repeated compression and relaxation of the planet's shape. As the gravitational force intensifies when the planet swings closer to the star, the planet is squeezed. As it recedes to its maximum distance, it relaxes back toward a more spherical shape. This constant kneading generates internal friction throughout the planet's interior, and friction produces heat. Scientists have calculated that tidal heating could warm TRAPPIST-1e's interior by as much as 0.18 watts per square meter of surface area. This might not sound like much, but it represents roughly 24 times the tidal heating flux generated in Earth's interior. For comparison, Earth's internal heat flow averages only about 0.087 watts per square meter, yet this is sufficient to drive plate tectonics, power volcanoes, and keep our outer core molten and generating our protective magnetic field. We observe a similar and far more extreme process occurring on Jupiter's moon, Io. Io is tidally locked to Jupiter and possesses a moderately eccentric orbit. More importantly, it experiences gravitational interactions with Jupiter's other large moons, particularly Europa and Ganymede. These interactions constantly perturb Io's orbit, stretching and squashing the moon in an endless cycle. This tidal heating has made Io the most volcanically active body in the entire solar system, with hundreds of active volcanoes continuously erupting and resurfacing the moon at a remarkable rate. TRAPPIST-1e likely doesn't experience tidal heating as intense as Io, but even a fraction of that energy could have profound effects. Enhanced volcanic activity would continuously replenish the atmosphere with gases from the interior, potentially compensating for atmospheric loss to space. The additional internal heating would help keep the core molten and convecting, maintaining a strong magnetic field that shields the atmosphere from stellar wind and flare particles. This creates a potential feedback loop where tidal heating enables atmospheric retention, and the atmosphere allows for surface conditions that might support life. So where does all this leave us in our assessment of TRAPPIST-1e? We may be looking at an Earth-sized, volcanically active, rocky planet with the chemical building blocks for life already present, possessing its own substantial atmosphere and protective magnetic field, orbiting squarely within the habitable zone of a relatively calm red dwarf star. This would represent one of the most Earth-like worlds ever discovered, a true sibling to our own planet across the cosmic distance. Or, equally possible given the current state of the evidence, TRAPPIST-1e could be nothing more than a cold, dead, airless world, its surface scoured by radiation. Any water it once possessed long since evaporated into space or frozen into permafrost buried beneath a layer of sterile rock. A world that never developed life and never will, despite occupying what should be a prime location for habitability. The truth, frustratingly, remains unknown. Additional observations are required to resolve this fundamental uncertainty, to determine which of these scenarios, or perhaps some intermediate case, represents reality. We might not obtain a definitive answer until the proposed Habitable Worlds Observatory launches, a space telescope specifically designed to search for signs of life around stars more similar to our own Sunday. Current mission planning places this launch in 2041, 2 decades into the future. Until then, the James Webb Space Telescope's observations represent our best opportunity to characterize TRAPPIST-1. The mere fact that we possess the technological capability to measure the light absorbed by a thin gaseous layer surrounding a rocky planet orbiting a dim red dwarf star 40 light-years distant represents an almost miraculous achievement of human ingenuity and determination. Scientists have not given up hope. They have carefully studied the first sets of James Webb data, identified sources of noise and uncertainty in the measurements, and modified their observational techniques to achieve even more precise results. Another 15 transit observations are planned before December, each one adding to the dataset, gradually narrowing the error bars and constraining the possible atmospheric compositions. These additional observations should allow the research teams to confirm the presence or absence of carbon dioxide in the atmosphere, a key diagnostic that will distinguish between several competing models. The detection of carbon dioxide would strongly suggest the presence of a substantial secondary atmosphere, since this gas is commonly produced by volcanic outgassing and plays a crucial role in planetary climate through its greenhouse effect. The absence of carbon dioxide, conversely, might indicate either no atmosphere at all, or an atmosphere with a very unusual composition dominated by other gases. Perhaps TRAPPIST-1e and its 6 siblings will ultimately prove to possess unique atmospheric configurations that no one has yet predicted. Atmospheres that are inhospitable to life but fascinating in their own right, teaching us new lessons about planetary formation and atmospheric evolution around red dwarf stars. Perhaps one of these worlds will prove to have an atmosphere that could theoretically support life, checking all the boxes in terms of pressure, temperature, and chemical composition, even if life has not actually arisen there. Or perhaps, just perhaps, we will find an atmosphere nearly identical to Earth's own, dominated by nitrogen with substantial oxygen, that most reactive of gases which exists in our atmosphere only because photosynthetic life continuously replenishes it. The detection of oxygen, particularly in combination with methane, would constitute a powerful biosignature, evidence that biological processes are actively maintaining atmospheric chemistry far from chemical equilibrium. It is exciting, even exhilarating, to find so much potential for life in a location relatively nearby in cosmic terms, existing in the midst of what might seem like an extremely harsh and challenging environment. The TRAPPIST-1 system challenges our assumptions about where life can exist, suggesting that habitable worlds might be far more common than we once believed, distributed around even the smallest and dimmest stars. But whatever the atmosphere turns out to be, on TRAPPIST-1e, whether Earth-like or utterly alien, the search continues across multiple fronts. With recent discoveries on Mars, where certain rock formations have been identified that some scientists argue could not have formed without biological activity, the sense grows that the discovery of extraterrestrial life feels not just possible, but inevitable. The question that keeps astronomers awake at night, that drives mission planning and telescope time allocation, is not if we will find life beyond Earth, but when. Will it be on TRAPPIST-1e, orbiting its ancient red dwarf star in the constellation Aquarius? Will it be in the subsurface oceans of Europa or Enceladus, those frozen moons in our own solar system? Will it be on some world not yet discovered, orbiting a star we haven't yet studied? The universe is vast beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars, and we are only just beginning to survey the tiny fraction of nearby space accessible to our current technology. Every new observation, every refinement in our instruments, every improvement in our analytical techniques brings us closer to answering that most profound of questions. Are we alone? TRAPPIST-1e stands as one of our best current candidates for providing an answer, a world balanced on the knife edge between habitability and sterility, waiting for us to develop the technology and gather the data necessary to determine its true nature. The journey of discovery continues, driven by human curiosity and our deep need to understand our place in the cosmos.